change in rotational kinetic energy, and hence we can write it as half into I omega I square minus omega F square, that is final value and initial value difference. We have a cylinder whose mass is 20 kg and it rotates about its axis with angular speed that is 100 radians per second. We have to calculate what is the work that has to be done to stop. So which means W is nothing but the energy stored and it is mv square. Hello everyone. Welcome to session 4 of chapter 7, System of Particles and Rotational Motion. This is Swati from Department of Physics, Vidhyaashram University College, the Temple of Excellence, Mysuru. Till the last session, we have discussed about the theory part of this chapter, and in today's session, we are going to solve few numericals related to the concepts what we have studied in our theory classes. The first numerical, 2 point masses 5 kg and 10 kg. They are separated at a distance of 2 meters. We have two masses 5 kg and 10 kg and they are separated by a distance of 2 meter. We have to locate the position of center of mass from 5 kg along the line joining them. So let us write a pictorial representation. We have a masses 5 kg and 10 kg. I will take it as M1 and M2. Say for example, this is 5 kg and it is 10 kg. Now they are separated by a distance of 2 meter. So here we have to locate the position of center of mass. So say for example, center of mass lies here. What is the position? At what distance it lies? We have to find it. So as we have already discussed in our theory class, the position of center of mass can be calculated by a formula m1 x1 plus m2 x2 divided by m1 plus m2. Since we have only two masses here, I have considered m1 and x1 is nothing but the distance of m1 from the origin and m2 is the mass of the another object. So our value of m1 and m2 is 5 kg and 10 kg respectively. So what is m1? Let us substitute the values. m1 is 5 kg and x1 it is at the origin, so it is 0, plus m2 value is 10 kg and it is at a distance of 2 meter from the origin, and we have m1 plus m2, that is 5 plus 10. So we will get in the numerator 5 into 0 is 0 plus 10 2s are 20 divided by 5 plus 10 is 15. So we will get 20 divided by 15. 5 3s are 5 4s are. So it is 4 by 3. So what is 4 by 3 value? The value of 4 by 3 is 1.33 meter from the origin or from the point where m1 mass m1 is located. So center of mass is located at a distance of 1.33 meter from this point. So the next problem is a disc of mass 200 kg. Mass of the disc is given 200 kg and radius 50 centimeter. So it can be written as 0.5 meter is rotating at the rate of 480 rotations per minute, that is 480 rpm. We have to represent this in seconds. So we will get 480 divided by 60, that is 8 rotations per second. So we have to calculate what is the work done to bring the disc to rest. So we have to find the work done to bring the disc to a rest position. If the disc is stopped in 11 rotations, we have to calculate the retarding torque acting on the disc. We have to calculate the value of tau on the disc when the disc stopped at 11 rotations. So now these are the given data. So we have to find the work done. So how to find the work done for a rotating object? It is nothing but change in rotational kinetic energy. W is equal to change in rotational kinetic energy. So the formula here is 1 by 2 I omega square. So what is this omega square? So omega square, we have to write the expression for change in rotational kinetic energy, and hence we can write it as half into I omega I square minus omega F square, that is final value and initial value difference will give us the change in rotational kinetic energy. But what's the value of I? To substitute in this formula, we must know the value of I, right? So the formula to find I is mr square divided by 2. So what is m? The mass, that is 200 kg, and r square 0.5 the whole square divided by 2. So we can cancel this, we'll get 100. So 100 into 0.25, which will give us the value 25 kg meter square. So this is the value of I. So let us substitute the value of I in this expression. We will get half into I value is 25 and omega I square, that is nothing but 2 pi f. The formula to find omega is 2 pi f. What's the value of pi? It is 3.14. So I can write it as 2 into 3.14 into f is nothing but 8 rotations per second. So 8 the whole square minus 0, because the final position is rest position. The value will be 0. So simplifying this, we can cancel 2 and 2 and we remain with, so 3.14 into 8 the whole square into 25. So the value will get it here as 3152.7 joules. So this is the total amount of work done that is to be needed to bring the disc into rest. We have even asked to find the torque, the retarding torque that acts on a disc when the rotating disc stopped in 11 rotations. So how to find that? We have a formula, work done is equal to force into displacement, that is W is equal to tau into theta. So we have to find the value of tau, that is W divided by theta. But what is theta? Theta is nothing but 2 pi into number of rotations, that is 11. So from this we will get 22 pi. So let us substitute in the above expression. We will get tau is equal to 31582.7, that is the work done, divided by theta value is 22 into pi, and the value of tau we will get it as 457. The unit is Newton meter. So let us move on to the next problem. A solid cylinder of mass 20 kg rotates about its axis with the angular speed of 100 radians per second. The radius of the cylinder is 0.25 meter. What is the kinetic energy associated with the rotation of the cylinder? What is the magnitude of angular momentum of the cylinder about its axis? So we have a cylinder whose mass is 20 kg and it rotates about its axis with angular speed, that is 100 radians per second. What is angular speed is denoted as? So angular speed is denoted as omega, that is 100 radians per second. The radius of the cylinder is given, that is r is equal to 0.25 meter. What is the kinetic energy associated with the rotation of the cylinder? We have to find the kinetic energy associated with the rotation of cylinder. What is the magnitude of angular momentum of the cylinder about its axis? We even have to find the angular momentum. What's the formula to find kinetic energy? So kinetic energy is half I omega square, or we can also write it as I omega square divided by 2. But how to find I? So I can be calculated as mr square divided by 2. So we will get mass as 20 into radius is 0.25 the whole square divided by 2. So we will get it as 10 into 0.25 the whole square, and the value we get it here as 0.625 kg meter square. So this is the value of I. Let us substitute the same in this expression to find the kinetic energy. So what do we get? It is 1 by 2 into I value is 0.625 and omega square. Omega is 100 radian per second, 100 square. So substituting all the values, we will get the value as 3125 joule. Since we are finding the kinetic energy, the unit is joule. We also have to find the magnitude of angular momentum of the cylinder about its axis. So the angular momentum for a rotating cylinder can be calculated by the formula L is equal to I omega. So what is the value of I? I is nothing but 0.625 and the omega value is 100. So we will get, so 0.625 into 100 is 62.5 joule second is the angular momentum of the cylinder about its axis. Okay, we'll move on to the next problem. A hoop of radius 2 meter. So radius of the hoop is 2 meter. Weighs 100 kg, that is M is equal to 100 kg. It rolls along a horizontal floor so that its center of mass has a speed of 20 centimeter per second, which is nothing but 0.2 meter per second. How much work has to be done to stop it? We have to find out the work done to stop the hoop. We know that the work done is stored in the form of kinetic energy. So what sort of kinetic energy here? A hoop is having a translational kinetic energy as well as the rotational kinetic energy. So the total kinetic energy can be calculated as the sum of translational kinetic energy plus rotational kinetic energy. So ET is equal to half mv square plus half I omega square. For a rotating body, the kinetic energy is stored and it can be calculated as I omega square divided by 2. So we know that I is equal to mr square, that is moment of inertia is equal to mr square. So we can substitute the value of I by mr square and we'll get the above expression as half mv square plus half mr square omega square. So we know that V is equal to R omega. We know the expression V is equal to R omega. We have R square and omega square here and we can write the expression as half mv square plus half mv square, because we have R square omega square. We know V is equal to R omega, so we can write it as half mv square. So we will get half mv square plus half mv square, that is mv square. So the total kinetic energy is mv square. We have to calculate what is the work that has to be done to stop. So which means W is nothing but the energy stored and it is mv square. So let us now substitute the values. M is 100 and what is the value of V? That is 0.2 the whole square. So 0.2 into 0.2 is nothing but 0.04 into 100 will give us 4. So what is the SI unit of work? We are finding out what is the work that has to be done to stop the hoop. So work done we are calculating and the SI unit is joule. So the total work done, we have to do 4 joules of work to stop the rotating hoop. So we'll solve the next problem. The angular speed of a motor wheel is inverse from 1200 rotations per minute to 3120 rotations per minute in 16 seconds. What is the angular acceleration, assuming it to uniform? So we have to find the angular acceleration. Angular acceleration can be calculated by taking the ratio of angular velocity to the time. So here angular velocity can be calculated as omega f minus omega I, that is change in angular velocity divided by time. But how to find the value of omega f? It is nothing but 2 pi final frequency, that is f2, and omega I can be calculated as 2 pi f1. So this can be calculated as 2 pi into what is f2? It is 3120 rotations per minute is given, but we have to find in seconds. So we will be dividing this with 60 and we get the value as 104 pi radians. The unit of omega is radian, and here similarly we will get the value 2 pi and f1 value is 1200 rotations per minute. So it is to be represented in seconds, so divided by 60 and the value we get it here as 40 pi radians. So let us now substitute these two values in the above expression and we will get alpha is equal to 104 pi minus what is omega I? It is 40 pi divided by the value of time, that is t is given, which is 16 seconds. So what is 104 minus 40? It is 64 pi divided by 16. So 16 ones are 16 fours are. So the answer will get it here as 4 pi radians per second square. So this is the SI unit of angular acceleration, that is radians per second square. So these are the few examples for numericals from the chapter System of Particles and Rotational Motion. So in our next session we will discuss about a new chapter. Until then, keep learning all of you. Thank you.